Hello everyone, welcome and thank you for joining us for this talk today. I'm Gilad, CTO at Valid Network, and today we'll be talking about blockchain security and the lessons learned. We'll cover various security events and incidents that occurred on public blockchain networks and see what we can learn from those events that occurred and how we can prevent issues similar to those happening in the future. Some background about Valid Network. Valid Network de-riskifies blockchain. We work tirelessly to help companies secure their operations and activity on blockchain networks of all types and the system in detecting vulnerabilities, mitigating risks, and handling incidents as they occur. We're powered by cyber and artificial intelligence, deep technology, and predictive analysis. A little bit of background about me. I'm Gilad Eisenberger. I'm co-founder and CTO at Valid Network. Previously doing cybersecurity and cloud security at Microsoft. And for the past few years, I've been doing blockchain security here at Valid Network, doing a lot of the research that we'll dive into today. I'm sure most of you have already heard the statement that the blockchain is secure. And that should pretty much end our talk today. But of course, the blockchain itself isn't really secure. At best, the blockchain offers a secure infrastructure on which you can run your applications and activities. The way that you utilize the blockchain infrastructure is your problem. There are concepts such as smart contracts, which are basically software applications that execute on top of the blockchain infrastructure. These applications have the same issues and vulnerabilities that any software can have. And any security issue in them is naturally the problem of whoever developed them and is maintaining them and takes a dependency on them. Unlike traditional software, there's no real central authority that's backing you when you utilize the blockchain. You're responsible for your own actions. There's no really way to undo anything that occurs. Sometimes you can get some help from the community, but basically it's all about you to ensure that the applications that you either develop or utilize are secure and have no security vulnerabilities in them. And to finalize everything, there have been billions of dollars lost in about 5 years that blockchain has been moving into the mainstream in various attacks of multiple types and over many, many years. And this should naturally indicate that this environment is anything but secure. There have been plenty of attacks and plenty of attack vectors, and these continue to occur and are very likely to continue to occur in the future. In this talk, we'll cover some of the events that occurred on the blockchain. We'll start with a few examples of how transactions work and how activity on the blockchain looks like traditionally. And then as we'll move forward, we'll start looking at malicious activity and attacks that occurred on the blockchain and attempt to learn from these events that occurred and see what we can do to avoid them in the future or in some ways mitigate the impact of these events. We'll start with some basic transactions to have a look at. These are, for example, on Ethereum in our case, but basically apply to pretty much any blockchain. So in the most basic case, we have a user A, Alice, that wants to transfer some funds, Ether in this case, to user B, Bob. And the way the blockchain works is that Alice would create a transaction defining who the funds are being sent to, the value being sent, and how much gas Alice is willing to pay to the miners for completing the transaction. And then Alice would sign that with her private key. That signature would verify the authenticity of the transaction and would basically identify Alice as the originator of the transaction and not someone else impersonating Alice. As a result, Alice can then send that signed transaction to the network, to one of the peers. It'll be distributed between the nodes, and eventually it will be mined by a miner in exchange for the transaction fee paid as gas. The miner will include that transaction inside a block and effectively update the state of the blockchain to the new state. In this case, it's transferring 10 Ether to Bob, and also reducing the gas fee from Alice's Ether balance, which will be transferred to the miner. Looking at this basic transaction, it's signed by the sender. Both the sender and the receiver are identified using the public keys, the public pair of their private keys. And the ether balance is maintained by the platform. In this case, Ethereum is replicated, so each node maintains a copy of the most recent state, and the consensus mechanism verifies that everyone's updating their state in sync and reflecting the same view of reality. And Ether is used to pay for these transactions for the effort to include them into a block as a way of maintaining the consensus. It's important to note that transactions can't really be stopped or prevented. So a signed transaction can be included in a block by any miner that chooses to. So given a sufficient fee, a miner will have the incentive to include the transaction in a block. And there's no real way to prevent a transaction from being mined into a block, as long as it's properly signed and isn't a replay of a previous transaction. The main risk around here is around the exposure of the keys. Since the private keys are used to identify the users and their identity, revealing the private keys could result in impersonation of the user. And that brings us into our first attack, which is the case of a stolen private key. In this case, we're looking at the KuCoin exchange that had an incident earlier in 2020. Where, in essence, a hacker gained access to the private key of their account, their hot wallet, as it's called, probably from their web server or some other location that private key was stored. I don't think it was ever exactly revealed how the attacker got access to that private key. And then the attacker can simply submit a transaction into the network, transferring any funds the attacker sees fit to his own private accounts, where the private key is only known by the attacker. In this case, there is nothing really that can be done to prevent these transactions from taking place, other than ensuring the key is not exposed. And this attack emptied out the KuCoin's hot wallet. So some of the funds that were used in ongoing transactions were basically emptied out of the account, with the balance pretty much being zeroed out. And a stolen private key basically allows anyone to impersonate the owner of the key, and transferring assets is pretty trivial in that case when you have basically full access to the account. The main ways to address this type of issue is naturally to protect your keys. This applies to any security system, not necessarily those that are blockchain based, but definitely on blockchain systems, it's important to protect your keys, ensure they can't be reached by incorrect persons. And another option is to look at recovery. So in this case, KuCoin had only some of their funds in this hot wallet, so the impact was indeed limited. They also operated quickly to attempt to freeze the funds and in some cases recover them as effectively as possible. So reacting quickly, identifying the issue quickly and reacting to it can help in freezing the funds and in some cases recovering them to limit the losses made as a result of the attack. Looking into a bit more complex of a transaction, we'll look at a token transfer. So in this case, we're looking at a token tracker. So this is a smart contract or a piece of code that executes on the blockchain. It executes as part of the consensus mechanism, so it includes basic logic that's executed and allows performing transactions that are more complex than a simple transfer of funds from user A to user B. So in this case, we'll look at USDT as an example, Tether token. We have user Alice, and Alice has a balance of USDT tokens that's stored by the token tracker in its state database. So in this case, we can see account A, Alice's account, has a balance of 100 tokens. And Alice would like to transfer some of those tokens to another user, in this case, account B, Bob. So Alice will create a transaction, and in this case, it's important to note that transaction has a value of 0 in the sense that it's not transferring any Ether or basic, the native currency of Ethereum, but rather it's performing an operation against a smart contract. So the actual value being transferred as part of the transaction is 0 in Ether. And we can see that it's requesting to invoke the transfer functionality, the transfer function, transferring from account A to account B a sum of 90 tokens. And there is a gas fee associated with this. Again, the miner needs the incentive to include this transaction as part of the block. So the gas fee is set to a certain amount to reward the miner for including that transaction inside the block. And this transaction is, again, sent out to the nodes, and then it's processed by the miners. And as part of the processing of the transactions, the miners execute the logic of the smart contract, in this case, the token tracker, which has an implementation of the transfer function, which will update the internal state of that token tracker and update the balance of account A to now be 10 tokens after transferring 90, and update the balance of account B to be 90 tokens after the transfer, assuming that account was empty before the transfer. Contracts are used to power non-native currencies and assets, and a contract is basically a piece of logic. A token tracker tracks the balances of each user in the token, again using the public keys and as identifiers or addresses. And the token tracker is implemented in code. In the case of Ethereum, it's written in Solidity, and it executes as part of the consensus mechanism, which ensures that the state is updated correctly across all the replicas of the blockchain. Code in the smart contract always executes exactly as it was written. The execution happens as part of the consensus, and there's consensus around the output or the result of the execution of the code. And so there is no way to intervene in the code and make it execute differently in some cases, and so on. Whatever is written in the actual smart contract is what will be executed when the transaction is mined into a block. And the data that's stored in the token tracker can't be changed by any mechanism other than the actual code of the smart contract. So any functionality that's written into the contract can be used by users of the contract by creating a transaction that executes that logic as it was written. And then logic that doesn't exist in the smart contract can't be used by anyone, and there's no way to change data in a way that isn't implemented in the smart contract. This gives a very good definition of how a contract behaves, specifically around how a token tracker would behave. So there are rules in place about how a transfer occurs, what are their prerequisites to perform a transfer, how it's executed, what are the results, which functionality is enabled, how are tokens created, how can they be destroyed, etc., etc. And this allows creation of assets by any definition using different business logic for the assets as the users or the creators of these assets see fit. Let's look at a few attacks that this new functionality brings in, and as we move into more complex behaviors, we start looking at more and more complex attacks and more complex malicious activity that can occur on the blockchain. We'll start with a pretty rudimentary utilization of a vulnerability in the smart contract, and this is a self-transfer attack. And it relies on a weakness in the actual implementation of the smart contract. So the code of the smart contract as it's written is sometimes vulnerable to various edge cases. In this case, the attack is actually very simple. The attacker transfers tokens to his own address. So from account A, transferring tokens back into account A. So we can see the attacker creating a transaction, requesting a transfer from account A to account A at the sum of 100 tokens. Again, this is a contract execution, so it's not actually transferring any Ether value, but there is a gas fee associated with it, which is relatively small. And now we can look at the actual code of the smart contract that appears at the top right, and we can see how the transfer function is implemented. And basically, it first reads the previous balance of the from account and the to account, and then it calculates the new balance for the from account, the account that's sending the tokens, and updates the state to reflect that new balance after reducing the amount of tokens that were transferred. And then it continues to calculate the new balance of the to account, the account to which the tokens are being transferred, and finally updates the state with that new balance. And this is where the issue lies. Basically, the update occurring that reduced the amount of tokens was lost because the balance was read before the update took place. So we're basically, the contract is using stale data that was read prior to an update as a means to calculate the new balance of the to account. So this would normally operate as expected. However, when the sender account and the receiver account are the same address, the update occurs on the same memory area or storage area, and the reduction of tokens is effectively lost and overwritten by a right to update the contract, the new balance of the receiver. This vulnerability occurred for several tokens, and while it seems basic, it does apply to several different contracts where it appears. Quickly looking at another attack that's based on a vulnerability in the smart contract, we will look at a batch transfer attack or a batch overflow attack. Here, a vulnerability in the smart contract in the specific function that allows a batch transfer. So a batch transfer is a transfer of tokens to multiple receivers in one transaction. The idea is because transactions have an associated gas fee, in some cases, in an attempt to reduce the cost of a transaction, contracts offer the option of performing a batch transaction where you'd perform multiple transfers in a single one and paying a significantly reduced gas fee since you're only executing one transaction. So in this case, we're looking at the beauty chain BC token that had a vulnerability in the contract where we're looking at the batch transfer function. Well, it calculates the number of receivers that are receiving that are expected to receive the tokens being transferred, and then calculates the total amount being sent to all of these users that are receiving the tokens. Now, in this case, the multiplication performed here is an unsafe multiplication in the sense that when it performs an arithmetic overflow, since these variables have a limited size, that overflow is effectively lost, and the result of the calculation becomes incorrect or inaccurate in terms of what the developer expected. In this case, the transfer requested transferred to two addresses with the amount of tokens that was enough to perform an exact overflow and reduce the outcome result back into zero. Looking at the logic of the contract as it continues, it verifies that the sender has sufficient balance of tokens to send to these users. Now, because the calculation overflowed, the verification is verifying that the user has more than 0 tokens, which is the result of the overflow, when in reality it should have been verifying against a much larger number of tokens being sent. And as a result, the contract incorrectly assumes that the sender has sufficient balance, although the sender has a balance of 0, and then proceeds to update the balances of the users that are receiving the tokens to their expected receiving value. This effectively creates data corruption in the contract storage itself, as the total number of tokens doesn't match what it was before and what the expected value is, since the state tables now include data that isn't correct, since it didn't update correctly the balance of the sender when it incremented the balance of the two receiver accounts. So both of these attacks are errors in the contracts and in the code of the contract. And effectively, the contract doesn't match the intended business rules that the author of the contracts expected to have. In both these cases, the contracts themselves are final. Blockchain doesn't really have a way to update contracts unless you leave that in advance, and there's no real way to update the contracts to remove this vulnerability or fix it. And these two cases can cause significant loss and have caused significant losses to several assets where this vulnerability was eventually exposed. Important to note that these issues can usually be identified, in some cases very easily. Unfortunately, since the blockchain is replicated and attackers can easily create their own replica of the blockchain, they also have visibility into the code of the smart contracts, and they can also identify these vulnerabilities as easily as anyone else, which allows attackers to utilize these transactions or these attacks in their favor. Another attack type is the front-running attack. The front-running attack is based on the blockchain's transaction pool being visible to everyone that's powering the blockchain, and all the node operators have access to view the transactions pool, which is a pool of pending transactions before they're mined that miners use to include into a block. So in the front-running scenario, Alice would like to submit a transaction, in this case a call to a smart contract, to redeem a gift that she received. So she'd execute the redeem gift operation and request the gift and provide a secret that was provided to her in order to redeem the gift. The contract itself simply verifies the secret and uses that to verify the identity of Alice, and then uses her address to send her the gift that she received. Under this scenario, the attacker can view the transaction while it's still sitting in the transaction pool waiting for a miner to select it to be mined, and submit his own transaction that has a higher gas fee than Alice's transaction. This higher gas fee rewards the miner more significantly for including the transaction into a block. And as such, it motivates the miner to include it into a block quicker than it would include Alice's transaction. So assuming the attacker can submit the transaction before it's mined, before Alice's transaction is mined, and the miner is more likely to include the attacker's transactions first. This means that the attacker can utilize the information in that transaction, in Alice's transaction, view the secret, and then utilize that in his own transaction that would then bypass or be submitted before Alice's transaction and execute against a smart contract first. This means the attacker can gain access to the gift that was intended for Alice and collect it before Alice's transaction is mined and effectively entered into the ledger and executed. Alice's transaction would later be executed. However, since the attacker's transaction has already executed, it's likely to fail, depending on the smart contract logic. And in this case, Alice wouldn't get the gift that was intended for her. So front running is basically part of the normal way of how a blockchain operates. The visibility that a blockchain provides to all of its peers and everyone that's working with the blockchain has its own downsides, where attackers can view transactions before they're actually entered into consensus and before they're executed, before they're final, and can utilize the information in those transactions to make their own transactions. Front running itself isn't necessarily illegal. It's not always unethical, but in certain cases it certainly is. It could include utilizing information about potential trades that others are planning to do, extracting information such as a secret that is included in a transaction, and other actions that that can be performed using information in pending transactions. Basically, the main conclusion is one, to be aware of this fact and the fact that any information in a transaction is visible before the transaction is executed. And that means to be very careful with secrets or information where you wouldn't want it to be exposed before the transaction is executed and before it's finalized. And have instruments in place, again, to facilitate recovery, help in addressing issues when these issues occur. And lastly, the ability to update or upgrade the contract, have that as part of the contract logic to allow you to supersede the contract with a newer version that would potentially not have the same issues or vulnerabilities if you ever identify them in the future. This allows you to address these types of attacks that are in some cases quite difficult to foresee in advance and handle ahead of time. It's important to note there are several front-running bots running on public blockchain networks where they simply monitor the pending transaction pool and look for transactions that the bot can execute in place of the original sender. That would net the bot a determined profit. If the bot identifies those, it immediately submits its own transaction that would have a higher gas fee, most likely be executed first, and net the bot a certain profit. These vary in their complexity, and sometimes they're able to identify quite complex scenarios, modify the transaction's data in a way that would benefit the bot, and then make a profit. Some of these are making good profit on the blockchain. Their morality is quite questionable and certainly something that anyone operating on the blockchain should be aware of. Another attack that we've seen, this one was quite significant a while back, is a lack of access control. In this case, we're looking at a Parity Multisig issue incident that they had. They had several incidents with this contract, and this specific one, after deploying an updated version of the contract, which utilized a library contract, which isn't directly executed, but its code is used in other contracts. During the deployment phase, the team deploying the contract deployed the contract and then forgot to initialize the contract itself. This wasn't a direct issue, since the uninitialized contract could still be used as a library contract by other contracts or other multi-sig wallets that depended on it. However, because it was never initialized, it was still open for anyone to initialize it for the first time. Effectively, the first account to initialize a contract becomes the owner of that contract. Or at least that's how the Parity Multisig wallet was implemented. The first initialized call sets the owner to whoever makes that call. Since the team forgot to initialize it themselves, that wallet was uninitialized and was left open for anyone to initialize it. A random attacker appeared and executed the initialize transaction on the contract and effectively became the owner of that contract. Now, normally that wouldn't have a significant effect, since that contract isn't used directly and only its code is used as a library. However, this specific contract had a functionality in it to allow it to self-destruct and effectively make that specific contract inoperable on the blockchain for future calls. Once the attacker, who is now the owner, invoked that functionality, which was limited only to the owner of the contract, the specific instance of this contract was self-destructed and terminated, and then it could no longer be used. Unfortunately, in that case, it can no longer be used as a library as well. So effectively, the attacker was able to take direct ownership of a contract that was never intended to be used directly, and then destroy it. By destroying it, the attacker limited the ability of other contracts to utilize that contract as a library. The result was quite a few wallets that had become locked, in terms that any functionality in them would no longer work, as they would call out to that library contract, and that call would fail because that contract was terminated. And this resulted in a significant amount of funds that were frozen and um, no longer operable, in terms that the wallets could never be, the funds in the wallets could never be extracted. So this specifically is a deployment or configuration issue. Looking at the smart contract source code doesn't really reveal any issue, so long as you initialize the contract shortly after deploying it and before actually using it anywhere. Ensure that you're the one who's initializing it, then everything should be fine. However, because the deployment or configuration of the contract was done incorrectly, a significant vulnerability was exposed. Another issue that was apparent in this contract is that there existed a single point of failure. So all of the different multi-sig wallets used by Parity all use the same library contract as their library for using the source for the smart contracts. And as such, when this was terminated, all of the wallets were affected. So it had a single point of failure that effectively executed a denial of service on all of these multi-sig wallets. So the natural takeaways are plan your deployment, make sure the configuration is correct, verify that extensively, not just the smart contract codes themselves, not just the software itself, but how it is utilized, and try to avoid a single point of failure. Not always that good of an option, but certainly be aware of single point of failures that can occur, and try to plan to see what you do if these failures do occur. So we looked at some attacks that utilize some basic transactions, and now we dive into more advanced transactions. As the blockchain is being utilized more extensively, the systems that it's running are becoming more complex, and as such, the interactions and the transactions that are being executed on the blockchain become more complex as well. So we'll look at a set of traditional transactions that are quite complex and functionality that's really started in the past year or so on the blockchain, and then dive into some attacks and incidents that occurred due to this. So we're starting with the basic functionality of these advanced transactions, and the first one to look at is a token swap. And a good example of this is Uniswap, which we'll look at a very high level. This process is much more complex than we'll be discussing here in these slides. But under a token swap, Alice would like to swap a token that she currently owns for a different token that she does not currently own. So Alice has 100 USDT tokens, and she'd like to swap those for another token. So in this case, Alice would submit a transaction to Uniswap. Uniswap in this case is the market maker, and then the exchange offering the ability to swap these tokens. Unlike traditional blockchain exchanges, this is a decentralized exchange. So it is completely powered by smart contracts. It is completely decentralized. It runs only on the blockchain, and it's interacted through via transactions on Ethereum in this case. So Alice would submit a transaction to swap 100 USDT for BNB token, Binance Chain tokens. And Alice would submit this transaction directly to the Uniswap router, which is the central smart contract powering the Uniswap exchange on the blockchain. And as a result of this, the smart contract code for Uniswap will in turn perform two other transactions from its account as a smart contract against the two token trackers. In this case, our token trackers are USDT and BNB. So Uniswap would start with performing a transfer of 100 tokens from Alice's account to the Uniswap account under USDT. So if Alice had 100 tokens, it would now be transferred to the Uniswap account, which would now have those 100 tokens in addition to its previous balance. after transferring these tokens, Uniswap will then calculate the exchange rate between USDT and BNB tokens, and then perform a transfer against the BNB token tracker, transferring the appropriate amount of tokens, in this case 300 tokens, for example, from the Uniswap account into Alice's account under the BNB token tracker. So as a result, Alice invoked a single transaction, which in turn had two sub-transactions or internal transactions that were performed by Uniswap that effectively swapped tokens. Alice provided 100 USDT tokens and in exchange received 300 BNB tokens. The swap is completely powered by a smart contract. It is considered very safe since it's performed atomically on the blockchain. And it utilizes the funds stored under the Uniswap account with liquidity pools, which Uniswap uses to power the swaps and enables the token swap without having a matching pair on the other side to swap it to do the other side of the exchange. The Uniswap simply transfers the tokens from its liquidity pools into the liquidity pool for USDT and then out of the liquidity pool for BNB. It's important to note that Alice provides Uniswap with allowance to make the 100 token transfer under her name. Normally you can't really just transfer tokens from Alice's account to the Uniswap account when the transaction is coming out of Uniswap, so Alice would initially need to give allowance to Uniswap to trade on her behalf against USDT to have the ability to for Uniswap to pull the tokens out of Alice's account. And since this is all powered on the blockchain, Uniswap has full verification of everything that occurs. If there's any problem with the transfers, there's insufficient tokens to make the transfer, Uniswap can simply cancel the transaction and revert all of the actions that occurred, and that will effectively undo all the effects of the transaction as if it never occurred, protecting the liquidity pools and allowing Uniswap to better control the assets that it's controlling. The token swap is powered by automated code, and one thing that's important about this this code is that it does the swap pricing. So this smart contract code needs to decide as part of a transaction what the exchange rate is between a pair of tokens. There's different ways to calculate or decide on the exchange rate, and that has several implications, as we'll see in the following malicious transactions in some cases. And as I wrote here, it's susceptible to manipulation in many ways. The code is very naive in terms that it executes on the blockchain itself as part of the consensus mechanism, and there's no chance for a person to intervene or say, hey, this doesn't make sense. There's a formula for how to calculate the exchange rate, and the code simply uses that formula to perform the exchange. Quickly looking at another very complex transaction. In this case, it's a flash loan. I assume some of you have heard the term in the context of an attack, but a flash loan in itself is not a malicious action. A flash loan is an action taken against a smart contract that provides a flash loan service, and effectively the idea of a flash loan is that a user can take out a loan that lasts for the extent of a single transaction. So the loan itself has a time span of 0. It's immediate in the sense that it's an atomic operation where the loaner contract provides the user with a certain amount of funds and expects the user to return those funds within the same higher scope transaction. So within the same transaction, the funds are provided to the user. The user gets an opportunity to utilize those funds as part of the transaction, and then is expected to return them still within the same parent transaction that's executing the whole operation. This allows access to a significant amount of funds in a way that's very safe for the loaning party. And we'll quickly look at how this interaction unfolds. So Alice would like to take a loan, a flash loan. So Alice would send a transaction to her own smart contract that Alice has provided for this specific operation. The smart contract would then borrow funds from a flash loan service, and that service would then transfer these funds to Alice's account as part of the transaction, and then call out to the Alice's smart contract, providing the smart contract with an opportunity to do something with those funds. So that smart contract could make a trade, for example, on an exchange, or make a series of trades, and take several operations within the DeFi space. For example, utilize an arbitrage loop to make a profit using these significant funds that were loaned, and would then, at the end of this sub-transaction, return the amount loaned back to the loaning service. After completing this sub-transaction, the loaning service would then verify that the sub-transaction indeed returned the loaned funds, including a set interest that's expected to be returned. Since all of this occurs under a single transaction on the loaning service, and that loaning service has the opportunity to cancel the transaction, to revert it. And that revert would cancel that operation and all of the sub-operations that occurred in it. That would include the initial transfer of the loaned funds, all of the trading that occurred, and the potential return or no return of the funds. What this means is that at the smart contract level, the loaning service has the ability to verify that all funds were returned as expected before the transaction ends. And if the funds were not returned, it can cancel the transaction and revert all of the changes made. This means that a flash loan is very safe for the party that's loaning the funds, in terms that if the funds are not returned within the same transaction, the whole operation is aborted, and there is no impact to the loaning service. And this means that potentially today, anyone on the blockchain can get access to significant amount of funds that could be tens or hundreds of millions of dollars worth of Ether or other tokens, use them for the scope of a single transaction, and then return them at a very, very low interest rate. Because the risk to the loaning service is very low, the interest rates on these loans are extremely low as well. In fact, the time where the funds are loaned out is effectively zero. That means that the interest rate is potentially very high if you look at the time scale involved. But at a numeral level, the interest itself is very low for a flash loan that's utilized. These types of loans can be used to increase the impact of a specific transaction, and including an attack. So if I were to find an arbitrage loop, for example, that would provide a 1% profit, where I could take 100 Ether and turn that into 101 by using a certain loop of arbitrage that I can make. If I can flash loan 100,000 instead of just 100 Ether, I can make a much more significant profit using the same loop, assuming all the calculations remain the same for a more significant number of funds. This means that one can utilize a flash loan to increase the profit in some cases, and to increase the effectiveness of attacks, especially those that are based on having access to very large sums of funds in order to execute the attack. What's also important to note is this is quite unique to blockchain. So the concept of a flash loan doesn't really exist in financial markets, and you don't normally have access to unrestricted loans that are anonymous, that allow you to gain a significant amount of funds for very short periods of time in a way that's very safe to the loaning party, and as such very cheap to the person taking the loan. After looking at these more advanced transactions, we can now start looking into attacks that utilize these more complex interactions on the blockchain network. And here's some more activity that occurred on the blockchain network. We'll start with the Reentrancy Attack, in this case the DAO, which was quite a while back. Um, in this case, we have a contract and an attacker that effectively used a vulnerability in the contract, a reentrancy vulnerability, to extract funds out of this contract. And we'll look at this interaction. It's a little bit complex, but I think we'll get through it. So the attacker starts by executing a withdraw operation against the DAO. So for the withdrawal, the user has an existing amount of tokens, and then the user withdraws those into Ether in response. So looking at the smart contract code on the right, the user withdraws a certain amount of tokens. The reward level is calculated and then transmitted into the attacker's account. Or into the user's account that's performing the withdrawal by effectively paying out that amount of Ether. What's unexpected here is that if the attacker's account is actually a smart contract, that smart contract has an opportunity to interact with the blockchain while it is receiving these funds. So during the payout operation, that smart contract can in turn execute other operations on the blockchain, including in our case another withdraw operation against the same DAO smart contract. Now, because the smart contract isn't expecting a withdraw operation while it is processing a previous withdraw operation, we can look at how it's calculating the balance that's expected. And because the previous operation never reached the update of the state indicating that the payout was actually paid out to the withdrawing user, it's looking at information that's not yet completely up to date. So it's calculating the incorrect balance for that user, and in turn paying out that user again, and calling out the payout. In this case, the attacker receives twice as many funds for a single withdraw operation. Once the second payout occurs, the attacker then simply needs to complete the transaction successfully. The innermost withdraw is continued first, and it'll update the state of the contract of the user's entry in that contract to indicate that the funds were indeed withdrawn. And then when it's completing the outermost withdraw operation, it'll update that state again, effectively slightly corrupting the state, since the withdrawn amount is larger than the amount that was expected to be able to withdraw by the user. In this case, the attacker can get out with more funds than were initially intended. And in this example, we show how there are two withdraw operations, one within another. However, the actual attack included a much more significant amount of nested calls into the withdrawal function, each of them withdrawing more and more funds out of the same initial amount of tokens that were obtained by the account. This allows the attacker to extract funds from the DAO, which has a shared bucket of Ether that's intended to be shared between its users. However, the attacker is able to withdraw more than intended for his account, matching his balance. In the specific DAO attack, this was executed multiple times, each with a very high nesting value, effectively extracting all of the funds, all of the Ether stored within the DAO smart contract, and cleaning out the account. These types of reentrancy attacks are a bit complex to understand. We can look at another example of an attack that utilizes a similar method but a bit different. In this case, while depositing funds into the account, the contract utilizes the balance before performing the deposit and the balance after performing the deposit to compare and understand what the amount of funds being deposited were for that transaction. In this case, by nesting the transactions as we see and calling deposit during the processing of a previous deposit execution, the attacker is able to confuse the contract into believing that the innermore deposit actually deposited twice as many funds as it did. Effectively, it is counted twice, once for the internal and then once for the external deposit, where it includes the funds from the external deposit, but also includes the funds in the internal deposit. This is a very similar case to the DAO one that we saw. Effectively, by calling into the contract while it is processing another operation, and while it still hasn't updated its state correctly, the contract is confused into miscalculating the amounts of funds that were either withdrawn or deposited or available for withdrawal. So looking at reentrancy as an issue, it's relatively easy to detect when it occurs. There's a very specific nesting pattern that looks very easy, very suspicious. It's also easy to track the data that's going on. However, it's quite difficult to detect these types of vulnerabilities ahead of time. There's a lot of complexity to the code involved in these attacks. The smart contracts are usually quite complex. And there's quite a few variables involved in detecting these attacks ahead of time. And this brings us to a topic of complexity to simplicity and comparing that to flexibility and security. These issues are quite easy to fix by reducing the flexibility of the contract. By not allowing certain operations, by limiting their behavior, by making them simpler, it is much easier to protect them. However, they become much less flexible, and they become unusable for certain types of scenarios that might be interesting from a financial standpoint. So it's important to understand exactly that every bit of complexity and flexibility added to the contract comes at the cost of an increased security risk. And as the contract becomes more complex, it becomes more difficult to protect it and understand what the security vulnerabilities in that contract are. Looking at another quite popular attack, and this one is based on the flash loans that we saw before, and it's an oracle manipulation attack, where the attacker manipulates the pricing calculation of an exchange using a flash loan. So in this example, an attacker would loan a significant amount of funds and then perform trades on a decentralized exchange, which would skew the exchange rate calculated on that exchange. The attacker would then utilize that skewed exchange rate to, for example, take out a loan, a non-flash loan, by providing a certain collateral and in exchange loaning out a different currency. Since the exchange rate calculated by the decentralized exchange is skewed, if the loaning party utilizes that decentralized exchange as an oracle to calculate the exchange rate between the collateral and the amount of funds being loaned on as part of the non-flash loan, these could effectively be skewed as well. And in this case, the exchange would provide a loan out that isn't really covered by the collateral provided, since it's utilizing a skewed exchange rate based on the decentralized exchange's skewed exchange rate. The attacker then just needs to reverse the two or more trades that were used to skew the price between the on the decentralized exchange, and that effectively returns the exchange rate back to normal, and then simply repay the flash loan using the funds that were returned by the reverse trades. This would naturally incur some kind of interest rate or exchange rate doing the transfers. However, the attacker effectively receives a skewed loan based on collateral that doesn't match the actual funds being loaned, and can then simply run off with that loan value that isn't matched by its collateral. And we've seen these attacks happen quite a bit on exchanges, utilizing miscalculations in how assets are traded and what the exchange rate between them is, to effectively make out with quite a bit of funds that are unmatched by collateral. And this type of manipulation can sometimes be difficult to detect. There are quite a few very complex transactions occurring today on the blockchain, and it's quite difficult to detect which are using skewed exchange rates and which are just performing complex transactions between several different tokens. And also, the legality of these types of situations isn't really clear. Effectively, the attacker is simply using an exchange and converting based on the set exchange rate. The attacker is certainly performing actions that would skew that exchange rate in a way that's probably not intended. So it certainly seems that's an inappropriate behavior. So that about finalizes what we wanted to talk about today. I just wanted to go over a few key takeaways to end the talk today. I think we've shown there's a lot of room for attacks. Certainly the assumption that the blockchain is secure and operations on the blockchain are secure by nature is completely incorrect. There's a lot that can happen, and basically it's about being aware of the threats that exist out there and that could affect your business operations when using blockchain technologies, just like with any other technology. You need to be prepared, act to eliminate vulnerabilities and reduce the attack surface, similar to what you do in any software system, and be aware of the risks throughout the system. I'd like to thank you for joining us today. Please feel free to reach out with any questions. My email's right here on the slide. And I'd love to hear from you. Any comments, thoughts you have, questions, feel free. Thank you.